So last two pages, 7.4. We brought this up yesterday when we were working with vectors. We were eventually going to get into these terms of I and j, which is basically their way of identifying their x and their y values. Okay, so it's just a different way that we can go about expressing vectors. But at the end of the day, they're still just vectors. So let's let some vector b be the component form of a comma b. Okay, this is the first notation that we learned yesterday. The most common again. And now we're going to write this in terms of I and j. And it's kind of like the complex numbers that we were used to. We had a plus bi, where we just used the I to indicate the complex part, and the real was obviously the other component. But here we've got, again, two parts, the A and the B, identified with the I and the J. So you'll kind of see here today and later on why we like to use the I and J. Again, they kind of have their time and place. But it's fairly straightforward. Don't make more of it than what it is. There we have our component form, 12, negative 1. We're going to write that in terms of I and j. 12 is the I. Negative 1 is the j. Again, it's still a vector. 12 units to the right, going down 1 unit. Go ahead and work on B if you would. They give us vectors a and b in form of I and j, and we just want to write negative 2a minus 4b. Good review what we did there yesterday. So as you're finishing it up, hopefully yours is looking similar to mine. Multiply by the negative 2 and multiply by negative 4. I went ahead and multiplied by the negative 4. That way I didn't have to worry about that negative later on. But yeah, there's your two vectors that you come up with. Same concept, add your x's, add your y's. 21.2 and negative 27. So 21.2 is your I, negative 27 is your j. Same as yesterday, all good? So probably the most, I want to say, beneficial use of vectors is when it comes to force and work. Is anybody taking chemistry? Did you use vectors for force, and did you talk about that? Maybe that wasn't Chem 2, maybe? Has anybody worked with work and force? No? All right. That's okay. But anyways, probably the most practical use of vectors is when it does come to our force and our work. So these first couple of definitions we've already had. The magnitude of V is equal to square root of A squared plus B squared. Magnitude again is your distance, okay? And again, distance the magnitude we typically think of as the distance, and that's going to change just a little bit today. We can use some other ideas with it too. A is going to be equal to the magnitude of V times cosine of theta, because that's your x value. Think of it as x is equal to r times cosine of theta. And then B is equal to the magnitude of V times sine of theta. Think of that as your y is equal to r times sine of theta. So we've taken the skills that we've known for the last couple of weeks, and now we're just incorporating magnitude with it. Because again, it's going to make a really nice connection for us today. And then this last one, there's quite a bit going on here. Vector, there's component form a comma b, which by substitution, since a was equal to the magnitude of b times cosine of theta, we can replace it there and there. But probably the best one today, or at least for the next couple of examples, is going to be this guy right here. And this is where we start applying work with it. How much force is needed to be able to pull an object. And then what if it's not in the same exact direction? Maybe it's at an angle or whatnot. how are we going to incorporate that? You know, if I got to pull something at a 45-degree angle, but it can only move horizontally, obviously the amount of force that I applied isn't going to be directly applied to that object. I'm going to lose some of that. Okay. So now we get to incorporate our angles along with the amount of force that we have with it. So let's go ahead and look at number 7. Got a man that's exerting a force of 80 pounds on an object by pulling on a rope at an angle of 30 degrees from the horizon. We want to write this force vector F in terms of I and J. So here we go. Let's draw the picture here to get us going. Here's our object. Got our 30 degrees with the horizon. Now it could be above or it could be below. Let's go ahead and go below. There's our 30 degrees that we've created. And again, 30 degrees from the horizon, so that's where that's the curveball of this thing. Going to the previous formula, F is going to be equal to the magnitude of our vector F times the cosine of theta I plus the magnitude of F times the sine of theta J. That's the formula that you copy down above. Nothing new there, I just replaced V with F. And now here we go. What do you suppose the magnitude of F is going to be? Any guesses? That's just going to be your 80. So usually up to this point, we've been having to do some work to come up with the magnitude. But now magnitude is just how much force we have. So nice and easy, direct substitution right there, 80. Okay, so again, think magnitude is, all right, what strength do I have? What's our force? Cosine of theta. Things get a little bit tricky here now, but we're still okay. You know, we draw in this 30 degrees, but if we go back to our angles of rotation, that 30 degrees in the grand scheme of things from 0 to 360 would be what degree measure? If we have it at this angle right here. No longer 30, but about 330. Does that make sense? So again, angles of rotation, 30 degrees from the horizontal plane means that puts us at 330 degrees. So when you plug in theta, it does have to be the angles of rotation that you know. 330 degrees, I, and then sine of 330 degrees, J. Yep, unit circle. Go ahead and take those out. Cosine of 330, x value at that location. Yep. And then 80 times the sine of 330, y value there. I think it's -1/2, right? And now just simplify your I and your j. J plus negative, and I should have just went -40. So if you want to write -40, you can. Obviously, same difference, but there we go.
What is the J on that side?
Oh, did I end up flopping him? Oh my gosh, why did I do that? Good question. Yeah, we don't want to do that. I, and then J. There we go. So let's just take a moment and understand what we did here now. Basically what we did was we identified the point in which we were going. You know, if we were to plot this xy, x 40 square roots of 3, and then negative 40, there it is right there. And while it doesn't seem like much, it's still your a and b, your x and y, and that's your what we consider the force vector. Okay?
Mr. Dorf,
Yep.
how'd you know to go like 3 degrees below the horizon line?
That's a good question. I didn't explain this one very well. We'll see in the other ones. It'll be a little bit more clear where to go with it, but yeah. I needed to type that up better, or they needed to kind of explain that better. They should have said, I think what I missed was 30 degrees below from the horizon. Okay. But again, what's the length of this vector? Let's kind of finish this thing. What's the magnitude, did we say? That was 80, right? We had an original force of 80. So if you want to fill that in there, maybe that makes a little bit more sense. That's where the 80 came from. But what we found was the x comma y that got us that length of 80. Starting to come together? Okay. We definitely got some more that we're going to look at today. So if you didn't get it the first time, it's all right. It's coming. Ball is thrown from a height of 1 meter. At the time of release, the velocity of the ball is given by the form or the vector, where each component is given in meters per second. We want to find the initial velocity, which is v sub o, and the angle theta above the horizon at which the ball was thrown. Good example for our notes here. Here we go. Let's start with that initial velocity. Initial velocity. Okay, essentially what we're looking for is that magnitude. And just understand what's given here. You know, we have that IJ form, which is basically component form. If we have component form, can we find the magnitude? Yeah, okay. That's just your a squared plus b squared. So our I value being the 27.2, J value 12.7. Calculator work from there, but again, initial velocity of that vector magnitude 30 meters per second. Let's go to the angle. So again, we're kind of recalling a skill that we had done before. When we wanted to solve for the angle, which was theta, what did we end up using? Which trig function? Tangent. Yep. Theta was equal to the inverse tangent of our y over our x, or in this case our b over our a, or even better yet, j over I. 12.7 over 27.2. It's going to be a lot of calculator work now, so that's good news for you. You can start using the calculators more. Unit circles every once in a while, but definitely a calculator one here. 25 degrees. So again, let's go back and try to make some sense of this again. A ball is thrown from a height of 1 meter, and at the time of release, the velocity of the ball was given by that component vector, where each component is given there. We found the initial velocity, and now we also found the angle as to which it was above the horizontal plane. So here we are, 1 foot above, with the horizontal plane, 25 degrees. Magnitude, 30. And now let's go to number 9. Getting back to our nautical miles per hour. Plane travels with an airspeed of 400 knots at 20 degrees south due east. and encounters a wind of 50 knots acting in the direction of 30 degrees south due west. Express the velocity of the plane P relative to the air in terms of I and J. Going back to our basic information. Starting with the plane, right? They gave us the plane, and they also give us a wind or a wind speed. Starting with that plane, 400 knots, 20 degrees south due east. Okay, we can draw that. South due east, 20 degrees. And we're going to hang pretty close to that y-axis. There's that 20 degrees right there. 400 knots. Once again, we're going to go back to that formula that we had on the previous page. Our vector is going to be equal to, and again, they can call it the force vector or velocity vector. Magnitude of v times cosine of theta I plus the magnitude of v times sine of theta j. What's our magnitude of v here? 400. So again, now the magnitude is a rate. It's a speed. Seems like it's changing all the time. At first it was a distance, then it was force, now it's a rate. And that's the great thing about it, is there's so many different applications that can be applied to it. It's almost like you can let it be whatever you want it to be. Now we got to be careful. Theta, it is not 20 degrees, but instead going to be what? There you go, 290. We're 20 degrees past the 270 mark. So to indicate the exact location there, we do need to use 290. Nice thing is, once you got it for cosine, then you got it for sine. Let's go ahead and go whole number approximations there. Again, 290 is not going to be on your unit circle. Radian or degree mode here for your calculator? Degrees. So just make sure you're good with that. Make sure you see the DG up at the top corner. Hopefully you got your I to be 137 and your J to be negative 376. You know, before we move on, let's because you're going to get into these and it's like, oh my gosh, did I even come up with the right thing? Like, does this even make sense? Just know what your I and your J represent here. It's basically your X and your Y, right? So your X is the 137. Okay, it's a positive value. Yep, we went to the right. But then I went down, and it looks like we went quite a ways down, all the way down to negative 376. And one more time, if you did the Pythagorean theorem with those two values, what are you going to come up with for a hypotenuse? 400, right? There it was. Okay, so again, the more connections you can make, the more confident you'll feel with it. All right, now we need to go to the wind. Okay, if we go back to the wind speed, 50 knots, acting in the direction of 30 degrees south due west. All right, so now still south, but now we're going west. Again, going to be fairly close to that y-axis. 30 degrees, there it is. Again, the wind speed, 50 knots. And now we got to do the exact same thing for that one. So take a moment, see if you can replicate B, what you just did for A. So once again, using our magnitude or force vector magnitude is 50. Our theta, not quite 270, but 30 degrees short of it, so 240. Plug it in and simplify. Negative 25i. And what'd you get for j? 43. So let's just, again, make sure we're good on what we did here. Back in part A, that was just, again, the plane itself, okay? Force vector there. Wind speed now, if we were just looking at the wind by itself, there's that force vector. Again, negative 25, makes sense. We're going to the left that many units. And then we went down 43. One more time, Pythagorean theorem with 25 and 43, we're going to get 50. And now this is where it's really cool. Now we want to find the true speed and the bearing of the plane. So think of it this way, drive down the highway, big side wind. What do you got to do when you get a big side wind coming at you? Got to lean into it a little bit, right? Okay. Big wind coming out of the north, you got to lean into it a little bit. Keep it straight, it's going to slowly start veering you off the road, right? So that's what we're calculating here. You know, plane's wanting to go this way, but the wind is acting in this direction. So where is the plane actually going to end up? So we're combining the two together. All right? And it's a relatively simple concept. Okay? Anytime you want to find the true bearing, you're just going to do the sum of those two. So we're going to call it R. We call it the resultant vector. You might have seen that in the GIM kit show up. But the resultant is just going to be V plus W. It's our I and J of the plane plus the I and J of the wind speed. J was 137I minus 376J. The wind speed, negative 25I minus 43J. And now as we add those up, the I's will get us 112I, and the J's, 419. So again, we call that the resultant vector, okay? This is where the plane is actually going when accounting for the wind speed and setting our original destination, okay? True speed, let's go ahead and calculate that. True speed, true magnitude in a sense, what do we got to do? Do the square root thing, absolutely. Magnitude of R always comes back to the Pythagorean theorem, right? For like the 37th time now in the last month. Yeah, you're just finding the hypotenuse of that x and y. $434 knots. So are we going faster or slower with the true speed than what we were anticipating? I think we're going faster, right? Originally, we set the cruise control of the plane to be at 400 knots. And now with that wind incorporated, we're going 434. Does it make sense that we picked up some speed? Yeah, I think so. You know, if you go back and look at the direction of the wind, it was also blowing in a more southerly direction as opposed to a northward direction. So it's no different than when you commute or you drive, you know, if you got the wind coming behind you, You know, they call it that tailwind. Yeah, it feels like you're going a lot faster, okay? Going a lot quicker with a lot more ease. Same concept here, okay? Last thing we do want to find is our true direction. Now the wind is not going in this perfect straight line direction as the plane originally was. So obviously it's going to throw us off. Maybe not a lot, but by a little bit. Finding the direction. Inverse tangent one more time. Of, again, the resultant vector. Okay? 12, or 112, and then negative 419. Negative 419 being our b. 112 being our x. And what does the calculator give us? Yep, I agree. So let's give the bearing of that. Can you work backwards to get the bearings of negative 75 degrees? Negative 75 degrees going downward from 360. What does that leave us here next to our vertical axis? 15, right? 15 degrees south due east. That is now considered our true direction when we account for the wind speed. And again, if we go back and compare that to original angle of our plane, we originally set for 20 degrees south due east. We had a little bit of a wind coming from east to west, so it makes sense that it pushed us a little bit further west. Now we're down to 15 degrees south due east.